In this video, we are going to find all positive integers x, y, and z such that x cubed equals 3 to the power y times 7 to the power z plus 8. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. First, I'm going to move the 8 to the left side, so x cubed minus 8 equals 3 to the power y times 7 to the power z. I do this because then the left side can be factorized as x minus 2 all multiplied by x squared plus 2x plus 4 equals 3 to the power y times 7 to the power z. Then I can say that each of x minus 2 and x squared plus 2x plus 4 is a product of a power of 3 and a power of 7. So why not we write x minus 2 say as 3 to the power a times 7 to the power of b, while x squared plus 2x plus 4 equals 3 to the power of c times 7 to the power of d. Now notice that for this expression, x squared plus 2x plus 4, it can be rewritten as x plus 1 all squared plus 3. Now, if x plus 1 all squared were to be a multiple of 3, then actually it has to be a multiple of 9, and when it's added by 3, I can say that for this index c, there is actually an upper bound of it, is that this c can only be at most equal to 1. So for c at most 1, that means c can only take two possible values. One is 0 and the other is 1. These indices must be non-negative. Now, if c takes such a small value, then since x is positive is at least 1, then that means x squared plus 2x plus 4 is at least 7. And if d is at the same time very small, then it will actually contradict the fact that x is positive. So that means d must be at least equal to 1. This index is at least 1. Now, however, if we took a look at the greatest common divisor of x minus 2 and x squared plus 2x plus 4, then actually their GCD, I can make use of the Euclidean algorithm and make that to be equal to the GCD of x minus 2 and the remainder when x squared plus 2x plus 4 is divided by x minus 2, and that's 12. And we can see that this GCD must also be a factor of 12, and that does not include 7. So that means they do not share 7 as a common prime factor. If one of the indices of 7 is at least 1, now d is at least 1, that means the other index, b, must be equal to 0. So the first case is that z equals 0. Then the system becomes what we have done above. X minus 2 equals 3 to the power of a. And for the second equation, x squared plus 2x plus 4 equals 3 to the power of 0 times 7 to the power of d. So from this case, they're actually coprime. Then I'm going to make x the subject of the first equation and put it into the second. So 3 to the power of a plus 2 all squared plus 2 times 3 to the power of a plus 2 plus 4 equals 7 to the power of d. And simplifying, we have 3 to the power of 2a plus 6 times 3 to the power of a plus 12 equals 7 to the power of d. Now, notice that from the system above, we actually have a plus c to be equal to y and b plus d equals z. So in the first case, in particular, a has to be equal to y. which means it has to be positive. So then we can take mod on each term safely because all terms are positive. Now notice that I can take mod 6 on both sides. For the left side, we have 3 to the power 2a. While on the left, for d, actually it has to be equal to z, again positive. So again, we can safely take mod. But now it's congruent to 1 because 7 itself, the base, is congruent to 1 mod 6. But that's impossible because a is positive, so the powers start from 3 squared, and that's 9, 3 mod 6, and the period is just staying within 3 mod 6, so basically it's impossible. That means there is no solution for this case when c equals 0. Now let's try c equals 1. The first equation is the same, but the second equation is a bit different. It looks like this. So again, doing the same substitution. It's just that the right side has an extra multiple of 3. Now I'm going to divide both sides by 3, and that gives 3 to the power 2a minus 1 plus 2 times 3 to the power a plus 4, and that equals 7 to the power of d. I'm going to take mod 4 on both sides. Now 3 to an odd power now is equivalent to minus 1 to an odd power. So the odd has some use on the power, and I can quickly say it has to be minus 1. Now the middle term is just 2 times minus 1 to power a for the time being, and it's congruent to minus 1 all to the power of d mod 4. Now the interesting thing is, which is also one of the motivations why I chose to do mod 4, is that no matter what happens to the parity of a over here, no matter it's odd or even, which makes this power to be equal to minus 1 or 1, then for either case it's just minus 2 or 2. But when we do mod 4, they're actually the same. So that means I can just say, for example, plus 2 over here, and then it's congruent to minus 1 to the power of d mod 4. And in either case, we will have minus 1 to the power of d to be congruent to plus 1 mod 4, and that means d is even, and I can let say d equals 2k some positive integer k. So now things start to get interesting. The equation now becomes 3 to the power 2a minus 1 plus 2 times 3 to the power of a plus 4 equals 7 to the power of 2k. Now I can move the 4 to the other side. So the right equals 7 to the power of k plus 2, all multiplied by 7 to the power of k minus 2. At the same time, for the left, I can factorize and write that as 3 to the power of a times 3 to the power of a minus 1 plus 2 equals to this product. Now notice that for the expressions at the right, not both of them are multiples of 3. In fact, only 7 to the power of k plus 2 is a multiple of 3. So that means 3 to the power of a should divide 7 to the power of k plus 2, and 7 to the power of k minus 2 do not take any factor of 3 at all. Now from this, we can say that we can create inequality, which is that 3 to the power of a must be less than or equal to 7 to the power of k plus 2. And to make the equation remain balanced, we should have the other way around for the other two expressions. 3 to the power of a minus 1 plus 2 should be larger than or equal to 7 to the power of k minus 2. But now things start to get interesting, because the larger term, I should say, a lower power for the second inequality somehow becomes the larger number when comparing with the powers of 7. So we can try to make use of this to create some bound on the value of a. In fact, from the second inequality, I can add 4 on both sides and get 3 to the power of a minus 1 plus 6 is at least 7 to the power of k plus 2. And using the first inequality, this is at least 3 to the power of a. So these two expressions only contain the unknown a. Then we can start comparing. And so we have 6 to be larger than or equal to 2 times 3 to the power of a minus 1, because I can write this as 3 times 3 to the power a minus 1. So it's just a linear equation. And so 3 to the power a minus 1 is at most 3, a minus 1 is at most 1, so a is at most 2. And since a is positive, that means a is either equal to 1 or 2. And from this, we can also get the value of y, which is y equals 2 or 3. And we can bring this back all the way up to this equation. And we can check them one by one. If a equals 1, then we'll put this to the left side. It's 3 to the power 2 minus 1, 3 plus 2 times 3 plus 4, so that's 13, equal to 7 to the power of d. No solution, clearly. While if a equals 2, then 3 to the power 2 times 2 minus 1, 27, plus 2 times 3 squared, that's 18 plus 4, then 49 equals 7 to the power of d. So d equals 2. Now we can move on from this. When a equals 2, y equals to 3, and because b equals 0, then z is just equal to 2. And we can go all the way up back to x minus 2 equals 3 to the power of a, and get that x equals 11. So that means our final answer is that x equals 11, y equals 3, and z equals 2. So this is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.